Good morning, everyone. So I'll continue talking about physical processes shaping evolution of stars and gas. And today I'm going to give you two lectures. One will be continuation of yesterday. I'll finish the story, and I will start by explaining you, repeating the puzzle with which I left you yesterday, restating what the puzzle is, and then describing how this puzzle is solved, and also how the energetic processes that associate with accretion of gas onto the supermassive black holes and energy and momentum injection from young massive stars and galaxies affect galaxy evolution. So the theme of this lecture will be so-called feedback, injection of energy and momentum by young massive stars and active galactic nuclei. As you'll see, and as I'll try to show you, this process is the absolute key. That's the current consensus that's agreed by everybody who's working in the field. It's absolutely critical for understanding how real galaxies in observed universe form. Without this process, all attempts to simulate and model realistic galaxies failed, for the reason that hopefully will become clear. Originally, sort of talking about star formation, the physics of star formation, now as opposed to in the next lecture. But when I was thinking about preparing for these two lectures, I thought that the more natural order would be this order, talking about the feedback on a galaxy scale first, and then talking about what feedback does at smaller scales within individual galaxies and how it sets the gas depletion time, the tau SF that I was talking and used in the model. So that will be the second lecture today. Right, so the injection of energy and momentum. This nice picture that I'll return to shows the very strong, very hot bubbles around galaxies, and this is the effect of the feedback, and we'll talk about what it does. But first, I'll restate the puzzle that I left you with. I don't know if you guys realize that I left you with the puzzle yesterday, whether you were puzzled or not, but let me try to restate it and tell you what the puzzle is. I was talking about the cooling heating time yesterday. This time is defined as the thermal energy of the gas divided by the rate at which this thermal energy is changing, so either due to cooling or heating, depending on which one dominates. And the thermal energy, assuming that gas is ideal, which is a great assumption for plasmas in the universe almost everywhere because the plasmas are rarefied, and ideal gas assumption is very good, so it's just nkt divided by gamma minus 1. And the rate of energy change, the way it's usually stated, is it's n squared, because these functions are modulated or calibrated relative to n squared, because n squared is a process that dominates the cooling rate, two body processes, multiplied by the net difference between the heating rate and cooling rate. And this is tabulated by plasma codes that take into account all the possible processes that lead to heating and cooling. And we use the results to figure out what the rate would be as a function of gas density, gas temperature, and gas metallicity, the heavy element abundance. Now, what I'm interested in is to understand how this cooling time, if I choose a particular density that's the same for all halos. So I'll choose a density that corresponds to the typical densities near the virial radius of the halo, where density contrast is about 200 relative to the mean density of the baryons. So I'll be estimating the cooling time, or heating time if heating dominates, for halos at a fixed density across independent of mass, but the result will be dependent on mass because the cooling rate depends on temperature that enters here and also enters through heating and cooling rate because they also depend on temperature, right? And temperature does change when I go to halos of different mass, because halos of different mass have different potential depths. Potential depth is gm over r, and mass and radius are related by definition. The radius is just 1/3 power of mass because they are related by constant and constant delta and the mean density of the universe. So the mass and radius are related. Radius is mass to 1/3, so this whole expression is mass to the 2/3 power. And so this expression, density is independent of mass, all these constants are independent of mass, but temperature enters here, and temperature, if I consider the virial temperature given by gm over r, creates a mass dependence of this quantity. So here it is plotted as a function of mass. I showed it yesterday. From smaller masses, pretty much all the mass relevant to galaxy formation, And you can see that this has complicated shape that reflects the shape of this function mostly. And there are three regimes in this plot. So first regime is at the highest masses, where you see that at this density, the cooling time is longer than the age of the universe shown by the dashed line, right? So it's longer. It's 10 to the 10, 10 to 11 years, which means that if gas is heated by collapse, which is the general expectation, to this temperature in these massive halos, it will have trouble cooling because its cooling time will be longer than the age of the universe. The cooling is inefficient. But the cooling time rapidly drops when we go to smaller masses, and below the mass of about 10 to the 12, roughly 10 to the 12, the cooling time becomes short. In fact, it becomes for halos around LMC mass 10 to 11, it's just 100 million years, so it's extremely fast. Which means that even if gas is heated by compression and shocking during gravitational collapse, it will be able to radiate this energy that it acquires very quickly on a time scale that's much shorter than the global evolution time scale, which means that the gas will not stay hot, will not retain the energy, right? And so this is the second regime. The first regime, inefficient cooling, inefficient cooling here, and second regime, efficient cooling. Now, this is something that is not obvious the way it's plotted, but below this mass, I told you yesterday, this actually inflection point where the heating starts to dominate. So for smaller masses, this curve should be interpreted as a heating time instead of cooling time. So the fact that it's short means that the gas is quickly heated, it's not cooling. And so this is third regime for small mass halos where background UV and X-ray radiation is heating the gas even at low density, even at very low density, and therefore preventing it from cooling. So in other words, according to this plot, we can expect that cooling of gas will be suppressed in smaller mass halos here, in large mass halos, and will be extremely efficient in this intermediate mass range between about few times 10 to the 9 to 10 to the 12. Is it clear? There are three regimes, right? So do we see, this is a very simple estimate, but what do we see? Do we see something like this in simulations? And the answer is yes. This was an area and focus of a lot of research over the last 15 years to understand how cooling and heating interact during compression and gravitational collapse of gas. And this basic picture that we get from this simple plot, which is really a textbook plot, which was people were considering since late 80s from Rees and Stryker paper. And if you go into the textbook of Moore, London, Bosch, and White, you'll find a similar plot there. Right. So we do see that in simulations, when halos are collapsing, the gas is rapidly cooling, and that's what creates, so in this case, you see the temperature in this progenitor for Milky Way. The blue here is about 10 to the 4 Kelvin. The hot gas, the red gas, is about million Kelvin. And we see that when this object collapses, the progenitor for Milky Way scale object. So at redshift 0 it becomes 10 to the 12, but this is at redshift 3.4. We see both hot gas and the cold gas. So we see that the cooling is efficient because the gas, a lot of gas is accreting, is able to stay cold. But we also start to see at this particular moment, we start to see some hot gas, which means that the gas that's heated and is at low density is able to retain its thermal energy. It's not cooling efficiency. And I chose this moment because at this point, this progenitor has mass of about 510 to 11. So it's right at this transition between the two regimes, between the efficient cooling and the inefficient cooling. And so it's just starting to build up, to heat some of the gas at low density, starts to build up a hot halo that you see here. Again, trouble with the buttons. I shouldn't get too excited. Let me go back to it. And so we see a hot halo being built up. Let's see it in dynamics, in actual evolution. So here's this actual movie. Here, this movie was done by Oscar Gertz. This is a progenitor. We are looking at a volume of a few megaparsecs across, and again, the temperature map. The most massive progenitor is here, and you see that at this redshift, which is a redshift of 6, the whole picture brightens up somewhat from dark to blue. This is reionization. This is when the universe was reionized and the gas was heated, intergalactic gas was heated to about 10 to the 4 Kelvin. And right here, right at the redshift of 4, you could see that some hot gas appears, a hot halo gets to form. So let me show you this evolution from the beginning again. So at first, the gas is pretty cold everywhere, right? So the object forms, but it's dark, which means that its temperature is low. And you can see that there's no hot gas. The gas stays at a few thousand Kelvin. Reionization heats it up to about 10,000 Kelvin. And only at redshift above 5, you start to see some hot gas. And this hot gas, at first, has trouble staying hot. It forms, but then it cools again, so the temperature stays low. And only here, we start to see hot halo forming. And this is the epoch where this object reaches the mass where cooling time at low densities becomes long, where it transitions from this efficient cooling regime to inefficient cooling regime. And we see the hot halo building up, right? So on the surface, this works. So this transition, this mass scale is present in the simulation, and we see it in the development of a hot gaseous halo in pretty generically in simulations when the mass goes into this inefficient cooling regime. So we can try to incorporate this. We can try to assume, well, it's a reasonable assumption. In fact, this assumption was made by Reesen and Stryker, for example, and by many other people, to assume that, okay, so cooling becomes inefficient in halos above 10 to the 12, and therefore accretion of gas, because the hot halo builds up, becomes inefficient on the central galaxy as well. And so this process, just like UV heating after ionization that I considered yesterday, would introduce a mass scale into the problem, but much larger mass scale. Instead of 10 to 9, it would be mass scale of 10 to 12, right? Okay, so cooling and heating, the competition between cooling and heating introduces a new mass scale into the problem. And we know that when mass scale or time scale is introduced into the problem, it will get imprinted into the scaling properties of galaxies. So for example, scaling of stellar mass with total halo mass. We modeled it, such imprint when we consider the Jeans mass due to UV heating, and we can try to model this as well with this mass scale imprinted onto the using a similar smooth step function. So in other words, we modify the accretion rate from the total mass accretion rate, the baryons, by suppressing accretion with a smooth step above mass of 10 to the 12, above this mass scale, right? And you can kind of predict what's going to happen. We're going to suppress star formation and gas cooling at large masses. So I showed you yesterday that if I run the model with UV suppression, which has characteristic mass scale of 10 to 9, it has barely any effect on massive halos, actually no noticeable effect. But here I show you that if I introduce this model, I told you yesterday that you can try to implement it yourself, but now if you look at the repository, you'll find this model with this mHot implemented as a subclass in the Galaxy model code that's already there. So I added such function, and this here I just run it. And what you see is again the familiar plot with the total halo mass with two regimes, fast and slow, and then the stellar mass and the gas mass in this halo, right? And this is star formation rate. And this is a massive halo. It ends up with mass of a few times 10 to the 12. So it's in a regime where this process should be relevant. In fact, it crosses this time scale of 10 to the 12, or mass scale of 10 to the 12 right here. So pretty early on, at about 3 billion years, so redshift 3 or so. And what we see is that right after it crosses, the gas was happily increasing up to that moment. And then after the halo became larger than 10 to the 12 and this process kicked in, if we suppress the gas accretion, there's no new gas coming in, and the gas mass starts to decrease on the depletion time scale that I assume, so due to star formation, right? So now the gas mass has this peak at the early redshift and then decreases. And the star formation rate, which is just gas mass divided by a constant depletion time scale in this model, also acquires a peak with exponential decrease of star formation rate. You can see that even such massive object at redshift 0 has star formation rate of just a few solar mass per year. So the star formation rate is greatly suppressed because there's no gas from which to form stars. So this process introduced a significant effect on the evolution of massive galaxies with this assumption that above 10 to 12 accretion is shut down. And this is apparent in evolutionary tracks. And as Olga mentioned yesterday, observations of galaxies indicate that typical star formation history, especially of massive elliptical galaxies, does have a peak at early times and then decreases exponentially. So in this model, that's happening, right? Because the gas accretion is shut down, the star formation peaks at some early redshift and then exponentially decays. So it does what observations suggest us, and we have a physical process that kind of justifies this. Effect on stellar mass-halo mass relation that I was considering is very simple, because beyond certain mass in this model, we shut down accretion of gas, and so star formation slows down very quickly, exponentially, and the stellar mass growth is stunted above halo mass of 10 to 12. So 10 to 12 is right here, and with this process, I simply slow down and stop the growth of stellar mass, and the stellar mass-halo mass relation flattens. If I compare it to the relations suggested by observation, shown by this orange line, I can see that I'm getting close at high masses with this process, but the slope is not right. The observations tell us that stellar mass continues to grow, whereas in this model it just stays flat. But that's actually okay. So, we could try to consider other processes to try to reconcile them, but there is a reason to think that this reconciliation may happen for other reason. And what is this reason? The reason is that in this model, I'm not considering mergers of galaxies. I'm simply considering evolution of gas, that gas turns into stars, but there is no mergers that bring in stars into the galaxy. It turns out that this is a very good assumption at small masses, but at high masses it's not, because the mergers of massive galaxies, they bring a lot of stellar mass. In fact, it is thought that for groups and clusters in this regime, 2/3 of the stellar mass of final galaxies comes from mergers and not from in situ star formation. In other words, this difference that you see between orange line and these lines could be due to mergers that were not included into the model. But the model gets pretty close in terms of suppression of stellar mass from where it used to be, close to this dotted line, to the observed. And then if we considered mergers, we could try to reconcile the slope of this line together. But we can see that this process doesn't do anything below 10 to 12 because it operates above 10 to 12 solar masses, so it cannot fix any discrepancies we had at smaller mass. So that's the first thing. The second thing, which is actual puzzle that I tried to state yesterday, but let me restate it, is that the simulations of galaxy formation that include all the cooling and heating processes that I was considering, and which should have imprinted this sharp scale into the problem. So I assume that they do this in the model, right? I assume that above 10 to 12, the gas accretion is suppressed because the cooling time becomes long. And the model tells me, well, I should see this scale very clearly because I assume that it's there. But in simulations that include all these processes, cooling, heating, right, we should see this scale as well. That's not the case. So this plot shows stellar mass of a central galaxy as a function of halo mass, so pretty much similar plot as before. This shows relation indicated by real galaxies. And the red lines of different types and these red points are results of simulations. The dotted line here again, the maximal possible efficiency, stellar mass proportional to halo mass with universal fraction. And these different points and different lines show simulation results that include all the cooling, all the heating, all the complexities of galaxy formation. But you can see that the result they produce is not that different from the simplest model that we use, right? They produce stellar masses that are close to this maximal line with almost linear relation. And if we look at this mass scale that we expect to be there, imposed by the cooling process, competition between cooling and heating, at this mass, there is a weak deviation from linearity, right? Here it's completely linear. Then we start to see that relation deviates, but there's nothing like a sharp transition that we assumed in the model, right? So there's simulation something else going on, despite the fact that they build up hot gaseous halos. And the gas at low density has trouble cooling. Somehow, the simulated galaxies in this case, in this simulation, still were able to convert most of the accreted gas into stars. It was showing at least only weak scale, only weak effect on the scale of 10 to 12 that we see. So instead of sharp transition, we see only a weak slight deviation that starts at around 10 to 12. So that's a puzzle. So why simulations that include all the physics that we considered and that we could expect to introduce a strong mass scale into the problem do not do this. And this puzzle is real. People were puzzling with it. You can see that all the simulations are relatively recent, 10 to 12, 10 to 14, 10 to 12. So just 6-7 years ago, and this was a source of great anguish that after running these complicated simulations, we're getting something that's not that different from the model, which includes 3 differential equations, right? And also why we're not seeing this sharp mass scale. The explanation turns out to be simple, although solution to it is anything but simple. And the reason is simply because we consider the cooling time only at a single density. And that density I assume to be close to the virial density of gas. Some of the gas that's heated during gravitational collapse is at that density, and that's why it's able to retain energy, and that's why the object, when it reaches a mass of about 10 to 12, is able to build a hot gaseous halo. But of course, inside that halo, gas is present at very different densities. And Anatoly showed you that we generally expect that matter, as a function of the virial radius, or delta, with density, will have profile that's pretty steep function of radius. And so even in these units at 1, at the virial radius, if we see some rho delta for the gas, this is a logarithmic plot, so it's log rho, log r. At smaller radii, the density can be orders of magnitude larger, right? So if I consider the same cooling plot at smaller radii, my cooling times will be short for the gas, even though they can be very long and longer than age of the universe at larger distances. So the gas that finds itself after collapse at these densities can stay hot, but the gas that tries to settle in equilibrium that will be compressed to larger densities here will have short cooling time and will continue to cool. As this gas cools and falls into the galaxy and accretes into the galaxy, an emptiness, the low density region forms in the center. Nature abhors emptiness, so the gas from larger radii will move in because the cooling in the center will lead to loss of pressure support. And so what will develop is so-called cooling flow. The gas will continually cool and continually flow onto the galaxy in the center. So that's why these simulations in which this happens naturally, because the cooling heating is considered at all radii, at all densities, are able both to maintain hot halo for the gases at low densities and continue to cool and form stars, continue accretion onto the central galaxy. In the end, essentially not modifying the result very much compared to assumption, when you consider that cooling is maximally efficient, which would be close to this dotted line. Do you guys have any questions about this? How this puzzle is explained? Yeah.
And how the observed relation was obtained? We don't know the mass of halos.
In some cases we do. So I showed yesterday a plot from our paper, but this is now became an active area where a lot of papers are published on determining this relation. And in many cases, statistically, in clusters you can measure masses, and you can measure stellar masses of galaxies. So in clusters you can measure masses from X-rays. And in smaller galaxies, people measure, for a given stellar mass, people measure halo masses through weak lensing by stacking, statistically. And so there are now ways to constrain and measure this line. The line itself is also comes from so-called abundance matching. This is something that Anatoly will be talking about tomorrow. But it's simply follows from assumption, it's simply nonlinear mapping between the stellar mass function of galaxies and the mass function predicted for the halos. If under assumption that every galaxy forms in a halo, we know that the stellar mass function has to be related to the halo mass function because each galaxy lives in a halo. And the mapping between those two functions that requires for there to be reconciled is this, so-called abundance matching. But it agrees, I showed the plot yesterday, it agrees with direct measurements of stellar masses and halo masses in the cases when we can do them. Does it answer the question?
Yes, but there were recent papers when the halo mass were measured with the extended H1 rotation curves. And just in this case, the relation between the stellar mass and halo mass for massive galaxies was up, not so shallow.
You mean when you add the when you
project by Stacy McGaw, about 200 nearby galaxies with the H1 observations.
Well, I have to compare their data, but I showed yesterday in a plot that can be found in slides for lecture 3 that if you look at a typical central, this is the mass of the central galaxy, and if you look at a typical central galaxy in a cluster or a group, so in this mass range, you see measurements of about 10 to the 12, right? And you can see that this line is roughly at 10 to the 12. So it is in the right ballpark here. Yeah, so this is a cluster regime. Now let's look at the Milky Way, so 10 to the 12 here. What is the mass it predicts? It's about 5 10 to the 10. So it's
and the baryon mass in hot gas is taken into account?
It's total mass. It's total mass. Yeah, it's everything.
It's total, and
this is just stellar mass. No, this is stellar mass of the central galaxy. So this is a relation between stellar mass of the galaxy that lives in the center of the halo and the total halo mass. So I'm just saying that remembering that in clusters and groups people find masses of about 10 to the 12. For the Milky Way, the mass is about 6 10 to the 10, so roughly where this line is. Say LMC is 10 to 11 and its stellar mass is 10 to 9, so somewhere here. So you can see that at 3 points this line actually is in agreement with those measurements that I remember, right? Which tells you that they can't be too wrong. Right. Any other questions about this? So a few years ago simulations were in big trouble because they were far away in this basic property, the stellar mass of a galaxy, they were far away from where real galaxies are. In other words, in a halo of a given mass, simulations were forming too many stars by a factor of several at least, even in the closest approach, but by orders of magnitude in the low mass regime and by at least an order of magnitude in the high mass regime. And at that point, we kind of knew everybody knew what the missing ingredient is, but nobody knew how to incorporate it properly. So that missing ingredient, which already you can guess from the subject of this lecture, is feedback. And first kind of feedback that I'll be talking about is particularly relevant for massive halos. It's the effect of feedback from active galactic nuclei, AGNs for short, which is associated with gas accretion onto supermassive black hole that usually is found observationally in the centers of galaxies, especially when we see quasar activity in the galaxy. And there are many examples of such black holes now. In our galaxy we have one of 2 times 10 to the 6 solar masses, but in massive elliptical galaxies these black holes reach masses of billions of solar masses, up to 10 to the 10. And one of the nearest examples is Centaurus A galaxy, so it's an elliptical galaxy with some dust lanes, so it's a famous case of merging going on with some gas and dust, but elliptical distribution of stars around them. And here shown in multivalence light, there is optical light as usual, there is radio shown by purple, and there is X-ray that actually is multicolor, probably determined by the temperature. But the point is that in addition to light, if you look at the light of galaxy, you see elliptical galaxy with a dust lane, and there is actually a weak optical jet, which can be seen, but maybe not in this projection. But in radio, we see very prominent jets, and then we see a lot of purple emission, which is non-thermal, so it means that it comes from some non-thermal component, and these are thought to be actual cosmic rays that fill the bubbles that extend to hundreds of kiloparsecs in this case. So we see jets originating from the very center of the galaxy, from the supermassive black hole, but then filling the space around the galaxy with energetic radiation, with energetic relativistic particles, and a lot of plasma flowing in some of the plasma in the form of ultra-relativistic cosmic rays. So we see that black holes can inject a lot of energy into surrounding intergalactic or circumgalactic medium. And so it's a natural assumption that this will do something to the gas, to the heating of the gas, and to the evolution of the galaxies. The problem is, what exactly does it do? There are many processes that can be involved in such violent flows. And if you're interested, there is a very nice review by McNamara and Nelson in Annual Reviews of Astronomy and Astrophysics, which goes one by one about all the processes people have thought about associated with jets, the bubbles that they grow, and the resulting feedback on the surrounding gas. And we don't know yet exactly how this proceeds. We're not certain. We have various scenarios, various models, but there is no certainty about which of them dominates. The certainty is that something, one of these processes, is working, because without it, like I said, simulations cannot prevent cooling of the halos near the center. And so even in order to explain why massive galaxies do not accrete gas, we have no problem explaining why low-density gas is not cooling, because the cooling time for it is short. But we have to have some heating source that heats the gas in the central regions of the halo, so that it does not create a cooling flow and some heating process that shuts down accretion onto the galaxy. And there is simulations that have been done, papers published almost every month, where people try to understand how this can happen, with pretty successful results now. I'll show you one example from the paper by Lee and Brian, which shows it's a not cosmological simulation, but something similar has been included in simulations of groups and clusters as well, into simulations of massive halos. But what you see here is so-called control simulation, where a hot gaseous halo is set up within the, in this case, the extent of this volume is just a few hundred kiloparsecs, because they try to model a central region of a cluster, so 10 to the 14 solar mass halo. So you see the temperature of gas in equilibrium initially inside the halo, and the temperature is mostly red with some yellowish in the center, and yellow color here is 10 to the 7, so it's 10 million degrees, with red being something like 10 to 8 degrees. And these are temperatures that are characteristic of the virial temperature of the cluster, because clusters are very massive and very hot objects. And this is initial state. This is how they set up the problem. And then they let it run by allowing also modeling cooling and heating, so the cooling is followed as simulation runs. They have a supermassive black hole in the center, which I don't remember what mass, but it's probably a few billion solar masses, which has a certain prescription, certain model for how it responds to accretion of gas. So when a certain accretion rate develops, this supermassive black hole starts to inject energy into surrounding gas. And you see what happens in this process. This is not my music, this is theirs. So let's first watch, and I'll walk you through what's going on. So you see that the end was very triumphant, with the music very triumphant, because what happened in the end? Everything became at 10 to the 8 Kelvin, right? Despite the fact that you saw cooling going on, so the formation of low temperature gas. So pretty much very quickly after the start of the simulation, you start seeing these cloudlets and pockets of bluish gas forming, and this is cold gas that's cooling. And the cooling is a complicated non-spherically symmetric process, and it happens near the center because the cooling time in the center is short due to high densities of gas. And when this gas cools, it acquires some angular momentum, so it forms a little disk. And this is the effect of their prescription for what the supermassive black hole does. So it injects energy and heats the gas, so it becomes very, very dark red, so very high temperature. And then after some point, the cooling can completely stop. So the whole evolution becomes this cycle of heating, then recooling again turns on and heats it again, and stops the cooling. So there is this balance going on between cooling and heating. So some cooling is happening, but it doesn't go into runaway mode, because the agent heating that turns on when the cooling starts eventually heats the gas and shuts down the cooling. And this balance creates a much smaller cooling rate and does result to the stunted evolution of the stellar mass. So the way we think this works is that a combination of inefficient cooling at low densities and AGN feedback at high densities is preventing continuing accretion and star formation of gas in massive halos. In other words, cooling is important, and this feedback is important. In addition to AGN feedback, I should say that people also consider feedback from supernova type 1a, even though everybody thinks that AGNs are dominant, but the massive elliptical galaxies are also filled with old stars, many of which explode as supernova type 1a, and that can also provide an additional rate of heating, which can be quite important. And we don't actually understand fully the relative balance between the AGN feedback and type 1a supernova heating. Here's an example. The simulation I showed you was like a toy model of in the controlled atmosphere of a cluster scale. But here's the result of a suite of cosmological simulations with something like what you saw in the previous simulation was included in the full context of collapse, in the full context of cosmological model. And essentially what you see here is the same relation between stellar mass of the central galaxy as a function of halo mass, with some differences. For example, you can notice that there is 500 here, so that's because they used over density of 500. I told you that people use different definitions in different papers. In X-rays, this mass is much more easily measurable than mass of 200, and therefore people use this definition. But regardless, it's total mass of the matter within some fairly large radius. And here, instead of stellar mass, they normalized it by this mass, so it's a fraction, it's the mass fraction. But the main point is that their simulation results, they're shown by points, and also this is their mean. And the central galaxies in their cluster that they were simulating, shown by these are essentially all galaxies, and the central galaxies in the cluster that they were simulating are shown by these field diamonds. They have fractions of mass, or stellar mass, to the total mass that are consistent with observational measurements in this mass scale, right, the gray points. In other words, with implementations of feedback that are phenomenological, but are included in the current suites of simulations. These simulations produce stellar masses of central galaxies in these massive halos that are consistent with observations. So in other words, their stellar mass was suppressed until it agrees with this observed stellar mass-halo mass relation at high masses. But inclusion of this process is phenomenological. That's why it's still a frontier of research. It's a complicated process. We still don't understand how it happens. Like I said, there's no understanding for how exactly black holes do this. Right now, simulations simply assume that in response to a given mass accretion rate of gas, the black hole injects a certain energy rate, at a certain energy rate. But this is just a phenomenological assumption. And it seems to work, so probably something like this works in reality. But we don't understand the detailed physics of this process. We also don't understand the relative importance of stellar heating by evolved stars, type 1a supernova and AGB, and the AGN feedback. So let me summarize this story. So for massive halos, the puzzle that slow cooling of gas at low densities was not resulting in a sharp mass scale that simulations were showing, which could naively expect, is resolved by the fact that in the law, at least we think it's explained by the fact that at high densities, AGN feedback and feedback from evolved stars is heating the gas, thereby preventing development of the cooling flow and continuing feeding of the gas and continuing star formation and growth of stellar mass. Are there any questions about this part? Okay, hopefully clear. However, as I said, this is all for massive objects, but at small masses, this is not enough, because a hot halo does not develop in the first place. So here we were talking about, what process is required to prevent gas cooling from the inner part of the halo, but there's nothing to prevent if there's no hot halo at all, if gas just free falls into the galaxy, which is what we expect in the low masses objects, because for such objects we saw that cooling time is short everywhere, so the gas has no pressure support at any radius. It has never a chance to develop a hot gaseous halo, and therefore it just free falls onto the galaxy, as we assumed in the simplest model of galaxy formation. So there the answer, the consensus is that it's also feedback, but it's a feedback most likely, and not from AGN feedback alone, but with a major contribution, or at least significant contribution, of feedback from young massive stars. When a stellar population is born, for example, a star cluster is born, the stars are born with a spectrum of masses, with a distribution of masses. The stars with masses above 8 solar masses will drive powerful winds and eventually will explode as supernovae within about 40 million years from the birth of the population. Both during the wind stage, when stars emit powerful radiation and also which drives the winds, both the radiation itself can inject momentum, as Daniel told you yesterday, and the winds can inject momentum into surrounding gas because they are driving the momentum in the wind. That momentum can be converted into energy through shocking, through internal energy. So initial momentum driving can become energy driving because the energy can be converted into the thermal energy. When supernovas explode, they do the same thing. Supernova remnants drive shells into surrounding gas, which impart momentum, but the shocks that are created by this blast waves of supernovae also convert the kinetic energy into the thermal energy. And so the overall effect of all these processes is to inject momentum and energy into surrounding gas by young massive stars. Of course, in order to have this feedback, you have to have star formation. You have to produce young stars continuously because that's what powers it. So this is a process that is relevant for galaxies that are continuing to form stars. And the poster child example of this process is M82 galaxy, also a relatively nearby galaxy. You can tell it because it's in the Messier catalog. It's a disk galaxy, but which forms stars at a fairly high rate, especially in the center. And this multivalence image of this galaxy, which includes X-rays shown by the blue here, and some ions in ultraviolet shown by red, show that there is something happens to the gas. There is very hot gas outflowing in the bubbles, and this is what's called galactic winds. So we see a gas outflowing from the regions of active star formation into the surrounding regions around the galaxy. So the gas is being driven out. And this is what called outflow, galactic scale outflow, or galactic wind. So we think that this is a process that's very prevalent at early stages of evolution of galaxies. And this is a process that fixes the discrepancies that we saw with the model. So how can we model it? The standard, well, first of all, because the process is related to star formation rate, so it's related to the rate at which young massive stars are formed, the outflow rate of gas has to depend on the rate at which young massive stars are born. So it should be a function of, so the outflow rate of gas from the galaxy in the wind should be a function of star formation rate. The simplest function, the simplest model is just a linear relation, so linear model. So the flow of gas out of the galaxy in the wind is proportional to the star formation rate with a constant that's called, well, it doesn't have to be a constant, it could be a function as well, but the proportionality quantity called mass loading factor, eta. That's something actually observers came up with this parameterization because it's quite simple. And people are trying to measure this relation in observed galaxies, which is very difficult, but nevertheless, for many galaxies, there is plenty of evidence that gas is outflowing, and these numbers are of order of one or a few. In some dwarf galaxies, it could be tens. But measurements of this number and observations is very difficult. Theoretically, though, we can justify that the outflow rate of gas should be proportional to star formation rate because it's driven by young massive stars, right? And this is the simplest model. Okay, so if that's the case, if we can assume this, and we have some model, some physical model for eta, and we can start with assumption, of course, no wind would correspond to eta 0, and we could start with a simple assumption that eta is just some constant value in the absence of any better guess or any better model. We can easily include this process in our model because we can modify equation for the evolution of gas in the interstellar medium of the galaxy, which before included just two terms, the mass accretion rate onto the halo modulated by these processes that we considered, UV heating and suppression of accretion in massive galaxies, star formation rate, and now we can add also removal of gas by these outflows into this equation, right? So it's a simple modification relatively in this model. Okay. So you'll find if you look at in the galaxy model, in the code subdirectory, in the current version of repository, if you pull the current version, you'll find a model implemented with this process, with this additional term. And the model is called simply model with wind. it includes several assumptions, several submodels for this eta parameter. But the simplest one that is where it assumes that eta parameter is a power law function of stellar mass, and I'll talk about why this is so before. So let me write it on the board. You'll see this later, but just so that you understand what parameters are. So this model assumes that eta is equal to some constant eta wind, then stellar mass in units of 10 to the 10 solar masses, but and to the power of alpha wind. So it's a power law model. So eta scales with stellar mass as a power law, and we can actually make it into no wind by setting this to 0, or we can make it into a constant eta model by setting alpha to 0, in which case it will be just equal to eta wind, right? So this model encompasses both a no wind scenario and also the constant mass loading factor scenario. So in this case, I'm running it with the same parameters as before, with the same star formation rate, depletion time of 5 gigayears, but with a wind model given by this equation that I call power law. And there are other models implemented there, but this is what I'm using here. With eta wind, with this constant here, equal to 3.6, and I'll explain why 3.6, but just a random number. And alpha wind to 0, which means that there's no mass dependence here, so this is just a constant eta factor. And then I run it for a grid of initial masses, and so I'm going to take a look at what it does to the stellar mass-Halo mass relation. So before we saw a large disagreement at small stellar masses without this, and so this is what you get for running this with a wind model with eta 3.6. And I don't know if you remember how it looked like, but this green line was very close to the dotted line, right, at this mass scale. And then a small mass was suppressed by UV heating, but at this intermediate masses, the green line without the wind was close to the dotted line. In fact, it's live, so we can actually rerun it. So I can just set it to 0. This will be no wind. Okay. And let's replot. So this is no wind. And what you can see is that, well, the shape looks similar, but you see that the green line is much closer to the dotted line, right? So what wind did with a constant mass loading factor is it suppressed stellar mass because it was constantly removing the gas mass in the outflow, so there was overall less gas mass available for star formations throughout the evolutionary history, and the stellar masses were suppressed. But because we assumed the constant that's independent of mass, we didn't introduce any mass scale into the problem. So the shape of these curves could not be changed. The shape of these curves right now reflects two processes. The UV heating at small masses, which imposes a mass scale of about 10 to the 9. The mass scale of 10 to the 12, which is a combination of inefficient cooling and supernova or maybe evolved star feedback. But between these two regimes, there's no mass scale, so the relations are still linear. And by introducing a constant into the problem, which is mass independent, we didn't introduce any mass scale, right? So that's why these curves did not change in shape. They just changed in normalization because we changed the amount of gas that's present in the galaxy, but we didn't change the shape. Does it make sense? Yeah? And that's why, when I put a wind with a constant factor, I move these lines down, but I'm not reconciling the shape. So you can see that the slope of this relation here is very different from the slope here. And just by varying eta parameter, keeping it constant, I will not reconcile those two curves. I can bring them closer, but they'll still have different shape. So we have to consider mass-dependent eta, right? And there is a pretty strong motivation for doing so. First of all, and this will be, I'll take the same approach as I did before. I'll show you a simulation result. And we'll use that in our model, and now I'll try to explain to you why this result, why this result makes sense physically. So in recent simulations, so there is a paper by Muratov et al. 2015, and there is a later papers that try to look into this problem, where the feedback was included from young stars, was included in the simulations themselves, they measure how much of the gas, what is the outflow rate of gas relative to the star formation rate, and they found that this mass loading factor, this eta parameter, scales with stellar mass. So this is stellar mass in units of 10 to the 10, and they found this scaling relation. So this is, you see why I assume 3.6, because it's normalization of their relation at 10 to the 10 solar masses, close to the knee of the luminosity function of galaxies. And there is a scaling with stellar mass. So it's negative, so it means that for smaller mass galaxies, as stellar mass is smaller, the eta is larger. So in other words, for dwarf galaxies, a given star formation rate removes more gas compared to massive galaxies. And physically, it makes sense because smaller mass galaxies have smaller masses, they have shallower potential well. And so the same input of energy, the same rate of supernova energy injection should be more efficient in removing the gas. And so just the direction of that scaling does make sense physically. In fact, the constant eta is what does make sense. Any questions? Yeah. Okay, so this is simulation result. This is, you can go into this paper, you can find a suite of simulations where they go and explain to you how they measured it. They show these measurements, but this is the final result that they get. And it works as they show for galaxies of different redshifts in all the simulations that they run. If they plot at any given redshift where they measure this thing, as a function of stellar mass, all the simulation results fall along this power law relation. Although, to say, I should say that the way the simulated simulation suite did not include massive galaxies. So even 10 to 12 solar masses were not included. So mostly what they probe is a regime of dwarf galaxies. So this relation, they calibrated for small mass galaxies and not for massive ones. So we can expect in general deviations from this relation for massive galaxies. So I still can use the same power law model in my run, if you can see it. Make it larger. So the parameters that I'm passing to the model is still, so I'm using the wind model, the same power law, with eta wind of 3.6, which is what they tell me they should be. And alpha wind is minus 0.45, but if you pay attention, you'll notice it's not 0.35. So let me change it. This was the result of experimentation. And let me rerun it with this parameter, minus 3.4. Minus 0.35. So I'm running it with the parameters exactly as they tell me they get in simulations. If you run it, you will notice that this runs slower because this process is very fast. The mass outflow rate is very fast, and so our ODE solver has more of a problem because it has to take smaller steps. The results are, let me replot it because it's probably for the wrong model. Here are the results. And this is live, so if you download the notebook, you should be able to run this on your own and play with the parameters. So this is the result of this, right? So we see that with the simple addition of outflow, with the power law model for the eta parameter that's calibrated in simulation, we get a result that becomes very close to this orange line at small masses, right? The shape and the slope may not be quite right still, so there may be some difference that we have to explore, but this is way, way closer to where real galaxies are compared to any other model. So we still had order of magnitude discrepancy before with a very incorrect slope. So here we're getting very close. Would you agree? Yeah? And I can make it closer. This was, I started off with this being minus 4.5. Because if I modify it, the results are quite sensitive to the slope. So it means that we can actually constrain it. So in simulations, there is choices that people make to measure this mass loading factor. So we shouldn't take simulation results as final truth because there are numerical issues, decisions of assumptions of how to measure this. And so they should be taken as a guidance. But in principle, we should also have a physical model that tells us what that power should be. And also, we can allow for some variation around that generally expected value. So if I run it with a power of 0.45, minus 0.45 instead of 0.35, the result will be even closer to observations. I'll show it to you now. For some reason it replots it. Yeah. So you can see that at high redshifts we getting really, really close, right? And you can say, well, that's fitting. I'm studying monkeys with a parameter, but that's, you know, for a model, that's a normal thing. I have a model, I can use the data to constrain the parameter. The question is, do I understand why this parameter has approximate value that it has? But it kind of tells you, this comparison tells you that maybe this process, the outflows with the scalings that are close to what simulations tell us, with this parameter being close to 0.4, is the explanation for the stellar mass-halo mass relation that we see for observed galaxies in the dwarf mass regime. Any questions here? Okay. And I should say that you can continue once you start modeling. You know, it's a rabbit hole. So you can continue refining the model. As I said, there are many other papers that are trying to quantify this factor, and there's a paper by pretty much the same group, but using more simulations that extend to higher masses by Daniel Alcazar, which have results that show that eta actually drops at a mass above 510 to 11. And this drop can be approximated by a formula like this, or maybe exponential cutoff, but this formula is pretty good approximation to it. So it goes to, in other words, this formula essentially makes eta go to 0 above certain mass, once it reaches certain value. And for this model, you can, if you run it, and this model is implemented in as modified, as it's called Murata 15 modified. So it's pretty much power law, but cuts off at high masses. And if you run it, you'll get it, you know, at reaches 0, this green line now, you know, traces the orange line pretty much across most of the small mass regime. So the model can be easily refined to give pretty good match to the simulations. But what's interesting is that whether we can also see that this model works for other things, right? So if we start playing with the parameter and, you know, just modifying it slightly and seeing that we can get better result, that's not very satisfying, at least not at the level of qualitative physical understanding. But what else this model gives us? What else does it predict? So first of all, you can see that it predicts for different redshift that this relation barely evolves, right? So on this scale, different lines at different redshifts are almost coinciding, right, in this regime. That's also what observations tell us. The stellar mass-halo mass relation at different redshifts, I didn't talk about it yet, but I'll show you the result. I told you that you need nonlinear mapping between halo mass and stellar mass in order to reconcile stellar mass function and halo mass function. But if you actually figure out what that nonlinear mapping is to reconcile the stellar mass function, halo mass function, you'll get this result that I was showing you at redshift 0. But this is a result of doing this at different redshifts, at pretty much at any redshift at which we have the stellar mass function measurement. So redshift 0 here is a dark line. It's somewhere here, but you can barely see it because lines at different redshifts are very similar, especially in this dwarf small mass regime. If we take normalization, if you take stellar mass divided by halo mass and plot so-called efficiency of star formation, so it's a mass fraction of the halo mass modulated by variant fraction that's converted into stars. It has a characteristic peak around 10 to 12, but you can see that the spread is very small. So there's barely any change in this relation between different redshifts. And the simple model with the wind captures this, right? So I showed you, sorry. You know, this is a prediction. I didn't do anything in addition, right? And it tells me that there's no evolution in this relation. It means that galaxies, as they grow in halo mass and grow their stellar mass, they just evolve along this relation, right? And I didn't do anything. I didn't tune the model, right? So this prediction is legit. It's a real thing. So it accounts for this process as being the right one because it tells us something that we didn't know before without any effort. This is how it affects individual galaxies. So this is a galaxy track for initial mass of 2 × 10 to the 6. I used it before because for this initial mass, the final mass, total mass of the object is 10 to the 12, so close to the Milky Way. And I was showing you yesterday, spending some time showing you that this model doesn't explain Milky Way properties. In particular, star formation rate was way higher, at 15 solar mass per year, and it didn't have a peak. And I couldn't fix this with playing with depletion time at all. So nothing, change of depletion time would never give me a low star formation rate because either depletion, when depletion time was short, I was having too much gas, too little gas, but depletion time was short and star formation rate was high. Or if depletion time was long, I had a lot of gas. And star formation rate was still high, but not because of low depletion time, but because of large gas mass. So the two were degenerate, and change of depletion time was not changing the star formation rate. And was over-predicted by a factor of 10, because for the Milky Way, we know that it's about 1 to 2 solar mass per year. And you can see this model, again, I didn't tune it, right? I was just putting calibration of simulation results, maybe played with a little bit with alpha parameter, but I didn't look at this yet. But in addition, it gives us the correct star formation rate for the Milky Way now, right? So it's about slightly more than 1 solar mass per year. So we did suppress the star formation rate for the same depletion time by a factor of 10. Because now, why is this? Because now galaxies has less gas, because a significant fraction of gas was driven out in the wind throughout its evolution. So star formation rate at higher reaches was suppressed. Instead of 30, it became, at maximum, it became about 2 or 3. And so the star formation rate was never high for this galaxy. The stellar mass that results is also relatively low. Okay? So, and this is another. So here's another result. I'm not changing the model. I'm still, well, maybe just different plots were made with maybe somewhat different. But I think it's actually minus 4.5 here. But the parameters may be somewhat different, but I'm not changing them significantly. And this is prediction for abundance of heavy elements as a function of stellar mass. Of course, to predict abundance of heavy elements, I actually have to model them. And so far, for simplicity, I avoided to even talk about this because I just considered gas mass, stellar mass, and the total mass. But there's nothing to prevent me from actually including the model for evolution of heavy elements. So this model is essentially adding an equation, another ODE to our galaxy model, which tracks mass in heavy elements, so mz. And this differential equation defines the rate at which mz changes. This rate consists of 3 terms. The first term corresponds to the accretion of gas. And the gas is assumed to be accreted from the intergalactic medium with some metallicity. I can set it to 0, and then I assume that the gas is accreted with just 0 metallicity, pristine. This allows it, right? But I can also assume that there is some pre-enrichment, for example, by first stars that I'm not modeling in the model, but should be pre-enriched in the intergalactic medium. So I can set it to some small value, for example. But in principle, it could be neglected as well. This is the main term that enriches the interstellar medium. This is star formation rate, modulated by the rate of return of gas into interstellar medium, with a factor yz that's predicted by stellar population models that tell me for a given mass of stars that are born, what is the yield or output of heavy elements that those stars produce. So such models follow stars of different masses and model the production of heavy elements in mainly supernovae, but maybe including some other more evolved stars. And they combine all the production into a single factor, yz. It's called the yield. And I assume it to be 0.07 or 0.069 in this model, which is a prediction for standard IMF from such models. As long as IMF is universal and constant, this number is also constant. And the third term is accounts for the heavy elements that are removed in the wind. So when gas is removed by wind in an outflow, it brings everything that ISM contains, including the heavy elements. And this is accounts for this. So it's proportional to the outflow rate of gas, E times star. And this is metallicity of the interstellar medium. So mass of metals divided by the gas mass. And so this is so-called Z parameters, the mass fraction of in heavy elements. And this accounts for how many of them are removed in an outflow. Assuming that the gas that's removed is enriched to the mean density, mean metallicity of the galaxy, which is an assumption actually, which is a pretty strong assumption, but a reasonable one. So it means that heavy elements at the time when the winds are removing the gas are well mixed with the interstellar medium. And you can actually model other process when they are not mixed, if when outflows are enriched relative to this by introducing another factor, but I'm not doing it here. And here is the result of computation you can find a model that implements such equation in the same file. Again, it inherits a class that contains all the other processes we considered, but adds this equation to the model. So it tracks another variable, mz, and has a function that describes the rate of evolution of mz. So after that, I can predict the same way I was predicting the stellar mass for halo mass. I can now predict mass of metals as a function of halo mass. I know also mass of gas, and so I can plot the metallicity with a ratio of mz to m gas. As a function of any other variable, I could plot it as a function of halo mass, but here I'm plotting it as a function of stellar mass because that's observable. And these three plots show observations. So there are magenta points showing measurements for two samples of dwarf galaxies. Some of them are satellites of the Milky Way. Some galaxies are nearby dwarf irregular galaxies. And moreover, some of these measurements are for stellar metallicities and some of the measurements are for gas metallicities. In the model, I'm considering the gas metallicity. I could have modeled also the amount of heavy elements in stars and plotted the stellar metallicity here. But observations tell us that in this regime at least, there's no difference. So measurements of metallicity at a fixed stellar mass in gas or stars are quite similar because both measurements are following the same relation. There are two samples here, in one case, the metallicity measured for gas, and in the other case measured for stars, and you cannot tell the difference between them. They are kind of following the same trend. And the three panels show predictions of three models. This model has no wind, so this eta is 0. And this was run in the notebook, so you can go and check these models. In this case, eta was 3.6, alpha set to 0, so it's constant eta. And you can see that at three different redshifts at which we have measurements for massive galaxies. Dwarf galaxies we only have at redshift 0. So the dashed lines show measurements of this relation for relatively bright galaxies that we can analyze and observe out to higher redshifts, even though those measurements are quite uncertain. But just to give you a sense of what massive galaxies are doing at different redshifts, those three lines show redshifts 0, 2.2, and 3.5 from Myelina et al. And the lines are redshift 0 dwarf galaxies, right? And the model predictions are also shown at 3 redshifts. And you can see that both the shape and a dwarf galaxy normalization in these two models is highly incorrect, right? So the model enriches the interstellar medium at all masses to a solar or fraction of a solar, and which is much larger than the measured metallicities of dwarf galaxies. This model, with this power law wind, without any additional effort, goes through the points, right? So it's again another point towards the evidence that this model has truth to it, because with no additional effort, by explaining the stellar mass and reproducing the star formation rate of galaxies, it starts reproducing other things. And actually, if you start looking at various properties, you can continue coming up with observables, with gas masses and so on. In most cases, if you compare these different models, this model wins by a long shot. It always is closest to observations compared to even wins with constant eta. So I would say that the constant wind mass loading factor is pretty much excluded if you make different comparisons. I don't have time to do different comparisons, so I'll just show you a couple to give you a taste. But the important thing is that I want to do before I finish this part is first to talk about, I presented it to you as a result of numerical simulations, but the question I want to ask and answer is whether we can make sense of it physically. And the answer is, of course, I think yes, because you can do a simple qualitative argument that would predict such scaling. I told you that direction of that scaling makes sense because for smaller galaxies, in smaller galaxies potential well is shallower, so for the same rate of injection of energy, it should be easier to drive the gas out for that reason, because the potential is, the ratio of the potential against which you have to work is smaller. I'll consider just one model, one assumption. In the notebook, you can find a couple of different models, but this already will tell you that you can understand the scaling in a relatively simple way. The model I'll present to you in the literature is called energy-driven wind model. This model, first of all, makes an observation that the energy injection from supernova should be proportional to the star formation rate, because young stars is what's producing the energy. It's called energy-driven because we're not considering momentum. We're just considering injection of energy by supernova. So this model assumes that the gas, the way feedback works, is that young stars are pumping energy into the interstellar medium. So interstellar medium acquires energy, right? Thermal energy. And then the second part is that this model assumes that this energy injection rate into interstellar medium results in the outflow, and due to energy conservation, the kinetic energy of the outflow has to be, or rate of that energy, has to be of order of the injection energy, right? Of course, in reality, we can have cooling losses, so on the way between the injection and the outflow, the energy can be decreased due to losses. So here it's assumed that even if such decrease happens, the overall proportionality between the injection rate and the outflow kinetic energy rate is retained. Then this model has the outflow of gas, the rate of outflow of gas, and the gas is outflowing some velocity, and velocity is assumed constant because when I take the derivative here, I assume that this is not changing. And the assumption, the key assumption that is made is that the gas is always driven out at velocity close to escape velocity from the given potential. So in other words, this V out is of order of escape velocity, which is -2 potential, or square root of circular velocity. Or for halo, it's proportional to mass divided by radius, so to the depth of potential well. And if I combine these things and I rewrite this equation again, I'll get the mass outflow rate, mass of halo divided by radius, but mass and radius are related by definition. They're related by a given density contrast that's fixed and the mean density of the universe. So the overall mass is proportional to radius of the halo cubed. And so mass by radius is just mass of the halo to 2/3 power. Right. So this is a scaling relation that this model predicts. And then by definition of the mass outflow rate, so the eta parameter is defined to be so mg out, the way we defined eta is eta times the star formation rate, right? So it means that eta is mg out divided by star formation rate. So I can take this mg out and just write eta, replace it with eta m star dot. So it'll be eta m star dot here, and this is proportional to m star dot. So m star dot will be on the left hand side, there'll be m star dot on the right hand side with eta, and m star dot will cancel out, which means that eta is proportional to inverse halo mass to inverse -2/3 power. So this is what's written here. So eta is predicted to be -2/3 power. So this is a numerical manifestation in this model, is the fact that for smaller mass halos, potential difference is smaller, and it's easier to drive the wind out. So the mass loading factor is larger. Then with a couple more steps, again, considering, for example, that assuming that the wind is efficient and pretty much all the mass gas, or most of the gas mass that ever comes into the galaxy gets driven out of the wind, we can replace the gas mass, we can integrate the equation and say that the total stellar mass integrated, so stellar formation rate integrated in time, will be proportional to the total halo mass, because the total gas mass that ever comes in should be close to proportional to halo mass, times this escape velocity, and if we collect the terms, and we can get that it's proportional to mass to the power of 5/3. And collecting these two results gives us eta to the power, it scales as a stellar mass to the power of -0.4. So in other words, we get from these arguments that the feedback is pumping energy into interstellar medium, that feedback is efficient, that outflow velocity should be always of order escape velocity, and you can ask me why this is a reasonable assumption. We can get a scaling that's very close to the simulation results. So in general, we can understand why simulations are showing us what they do physically. Now, in simulations where this process is modeled, energy is injected at star formation sites, and the injection and then the winds are developing self-consistently. This process does result in suppression of stellar masses, and the relation between stellar mass and halo mass, that's very close to observed one. So in that sense, what the simple model told us when we included results for from the simulations for the eta factor is very similar to what simulations themselves tell us in terms of the scaling relation. So here's the stellar mass as a function of halo mass M200 in two groups, just to show that this is the result that's obtained not by one group but by multiple groups. And there's more results like this, but these are representative, where simulated galaxies are shown by the blue points, whereas observations from different observational constraints from different methods and different studies that are summarized here are shown by lines. And this is pretty much the same type of relation that I was showing you before, saying that the real galaxies should be following this relation. These points now include the same set of physical processes in simulation of every single point that corresponds to a halo of different mass. There is nothing in simulation that tells that it should result in this scaling, but it emerges from the simulation for the reasons probably very close to why this happens in the model. Because we introduce a term that removes the gas mass at a given rate, and simulations tell us that it happens at a, with eta parameters close to power law function of stellar mass, and simulations reproduce this relation. So I showed you the simple model that it does this, but this actually happens in the simulations. And what's surprising is that the simple model actually captures this, because it just includes a term in the differential equation, whereas what happens in simulations when these winds develop is very dramatic. So I showed you a movie from Oscar Agert's. Let me show it to you again. That was done with parameters in which these winds do not develop. So the feedback essentially was not included in this model. So there is UV heating that happens, and then as galaxy grows, by creating more and more mass and by submerging, hot gas develops because at low densities the cooling time becomes long, and you see formation of the hot halo happening right around this epoch. That's already I showed you. And if we wait and we follow this evolution after this, pretty much all that happens is a continuing accretion of mass, continuing merging, and continuous growth of the halo. So this Gm over R, the potential depth grows, and we see that extent of the halo increases and the temperature gets higher. So the extent gets larger and the color, the red, becomes deeper. So the temperature grows. But qualitatively, nothing particularly changes. It's very relatively gentle process, despite the fact that it has shocks. But if the same simulation is rerun, the same object from the same initial condition is rerun with feedback, the way with the parameters that drive energetic winds, the evolution is very different. Even before ionization happens in this case, we see a strong explosion. In fact, they look like exploding bombs, where when galaxy forms and dense region creates an intense burst of star formation, gas is driven out in these very strong outflows, which actually go very far and heat the entire region. You don't even see ionization here because the entire region becomes heated by these winds. And as the galaxy continues to form, it now forms stars at much lower rate because a lot of gas got blown out, but as gas assembles during the continuous growth, new winds form. And so this process is continually driving outflows that you can see clearly here in the shocks. And as I said, what's surprising that the simulations that include this process that reproduce stellar mass-halo mass relations show that it happens in this very, very complicated form, but it's all captured in a simple term in the ODE equation because both such complicated simulation and the simple model that I was considering produces very similar results, right? So it all can be understood in terms of this basic physical process. And I think I'll stop here, right? And ask for questions. And I'll continue after coffee break, talking about depletion time. And I'll leave you with this movie. And also, if you'll come back after coffee break, I'll get another movie running. We'll show you what happens with these winds, not just for evolution of a single galaxy, but when multiple galaxies are evolving in the volume. Any questions, guys, on this part? Yeah.
So in the model, you said that you consider universal IMF. Now, there's been many articles about contradicting it, saying that the IMF may not be as universal as we thought. Do you think that, or is the model adaptable to maybe put in changeable, a variable IMF?
Yes, the answer is yes, it's adaptable because it creates a complication that you have to model that variation. But there were a number of papers in the last few years where people attempted to model variation of IMF. But observational evidence, in principle, there is no fundamental reason why IMF couldn't have varied very strongly in time and between different galaxies. In fact, the degree of non-variation is surprising because you can often hear a phrase, a term, universal IMF, universal initial mass function, right? Which refers to the fact that it doesn't seem to vary a lot. And what's interesting is that a lot of papers that point out to variations of IMF started to come out in large numbers around 2011. But in 2010, there was a review by Nate Bastian and collaborators in Annual Reviews of Astronomy and Astrophysics, which the whole review was about how people were trying to detect variations of IMF and couldn't. Right. So on the one hand, that review was kind of invalidated by subsequent papers, but at the same time, it collects a lot of evidence that IMF doesn't vary. Right. So both things are true. So for example, in the Milky Way, when we look at different star formation sites, we pretty much find the same IMF. If we look at globular clusters, which should have formed in a very different environments, across the mass range that we can probe in such clusters, the IMF still looks normal. The environments in which IMF was found, there is evidence that IMF probably is different, is pretty extreme. It's the centers of elliptical galaxies, not even the entire elliptical galaxy, but their centers. And the centers of elliptical galaxies are probably very special environments, because I'll mention it in the next part about star formation. Those environments were probably corresponding to extreme starbursts with highest surface densities, which are non-representative for majority of stars that are forming the new universe, but are probably what was happening when the centers of ellipticals formed. So yes, there is evidence for variation of IMF, but so far there are reasons to think that they probably these variations affect a relatively small fraction of the total stars in the universe, the centers of massive galaxies. Yeah.
Can I ask about this particular simulation?
Yeah, definitely.
What is the size of this box? Is it
well, so right, it's. I tell my students that whenever you show a simulation result, always put a box size, because you'll get a question about this, unless you want a question about the box size. And I'm violating this rule myself. By the way, this galaxy will drift out of the box. It's not very. But you can see that by redshift 0, all this violence stopped and it formed a nice gaseous disk. Let me show you another one, and I'll answer your question, because the box sizes here are comparable. This is another simulation from so-called FIRE collaboration from Hopkins et al. That you can find on their website. This will show you the gas density, and actually there's complicated color scheme here that encodes metallicity, density, and various other things. And you'll see that there will be a region here that seems to have an edge. This is not because gas has an edge in the universe, it's because this is a so-called zoom-in simulation that Daniel told you about. These simulations are focusing all of the mass resolution in the gas in a particular region, and what you see here is the boundary of that region, and then inside this region everything is modeled at the highest possible resolution. The second type of simulations, where you try to resolve uniformly the entire volume of the universe, these are simulations of the type of illustrious or eagle, but in this case I'm showing you evolution of individual objects in these zoom-in simulations that focus only on a sub-region of the universe. When we model galaxies like Milky Way, which was the case in objects of Milky Way scale, which was the case for the previous movie and also the case for this one, the progenitor, the region from which Milky Way forms, I calculated it in the first lecture, is a few megaparsecs. So when we focus on the formation of individual Milky Way objects, which is what was done in the simulations, the region that you're seeing is a scale of 2-3 megaparsecs. Yeah, come moving. Then it expands with the universe. You'll see that this region, when it starts, will expand, but then it will, at some point, start collapsing. But what you'll see is a qualitatively very similar picture where you'll see very violent winds. When the moment star formation starts and the dense gas forms, you start seeing these very violent outflows. So the color here is a combination of temperature and metallicity. Overall, what you see is density, but the color is actually metallicity. So this hot red thing is actually hot gas, and you see that this hot gas is constantly driven into outside the galaxy, where at some points the galaxy completely gets shredded, like here, and these are the outflows. And again, it looks very, very complicated. But remember, this scaling relation, the root of it all, actually came from these simulations. So in the end of the day, after all this complexity, what they measured is a simple power law relation. So a more complicated answer to your question, but allows me to show you another animation, which shows that this is a generic thing. So what you saw in the previous one, this complicated, very violent outflows, is also happening in this case. So it's not just one simulation. So let's break for coffee break, and I can answer any question. Yeah?
Just a small announcement regarding the materials for lectures. So we made a section on the web page of the school where there is a program and you can download slides and other material which lectures provided. And let me also ask lecturers to send updates because the school is going on.
And also, I'll use this opportunity to tell you, probably all of you should know by now, but I put all my stuff that I show you before the lecture on the same repository. I didn't put the movies there yet, but I will put these movies that you see in the PowerPoint as well, or at least links to them. But all the slides that I'm showing you are there already, in all the codes.